My name is Natalia Lupacheva, and this is Mark Penisten. We are with the Application Engineering Department with ATC. So we've been with ATC for about 10 years or so, 11 years, and probably in the last 5 or 6, we received thousands of LED products to be tested with our dimmer products for compatibility. So the need for this class came up. It's called the dimming unusual loads. So LEDs aren't really that unusual anymore. Pretty soon we're probably going to have incandescents called unusual, but in the future. But we still have problems controlling them. Who in here ever had any problems controlling LEDs? Oh, well, maybe this is a good class for you. How about that? So in the next hour or so, we will talk about why we have issues with LEDs, and maybe what tips and tricks we can give you to help. So, if this works, there you go. So we'll talk about components of LED fixtures, what LED is, how it's supposed to dim. We'll talk about traditional dimming, line voltage dimming, and other types of dimming. And we'll talk about our ETC compatibility testing. Then we'll have Q&A session at the end. So if you have any questions and it can wait until the end, can you please wait, or because we might cover everything during the presentation. So first, let's look what dimmable is. According to one of the manufacturers, I'm going to let you read through this. So basically, it means that you should be able to change the brightness. It doesn't say how low it needs to go, or how dim, or how it needs to. Sorry, got confused. How quiet or smooth the transition needs to happen. So in an incandescent world, we never had any standard measurement procedures for compatibility, because with incandescent lamps, we never had any issues. Now with LEDs, we have all sorts of issues. So NEMA came up with the standard called SSL7A. The standard is called the Basic Compatibility, and the purpose of it is so you should be able to take a compliant LED lamp and a compliant dimmer, and you know that they will work together. The downside is that this is the future-looking strategy. So it's good for new product going forward. It is not designed to see the compatibility between old product that's already existing. Also, a lot of manufacturers are pretty slow about adopting it. So ETC, for example, is not compliant yet. We're looking into it, but we're not compliant at the moment. Different companies have different ways of measuring flickering, and we will show you some of the examples of what ETC does in our future graphs. Flickering is also a non-descriptive word. It is used to describe all types of LED failures, like flashing or strobing, or hovering, shimmering, steppiness during fading. So all these are different types of failures, but all of them are described as flickering. So we need to know the difference between them, because every type of them will require a different solution. To understand why we have problems, first we need to see what LED is. LED is a complex load. It's not like a piece of wire, piece of basically metal, what the filament is, that you give it a power, it heats up, it glows. LED is complex load. It's basically two types of silicones joined together. One type has extra electrons, and another one has extra holes. And with a certain amount of energy applied, those electrons fall into holes, and that emits light. So it only emits light when the current flows one direction. It doesn't do anything when it flows the other direction unless LED is blown up. Here's the electrical characteristics between LED and tungsten. So as you can see, LED is, nothing even close to tungsten. This is our LED, and this is the tungsten, which is very close to ideal resistor. There is a different relationship between voltage and current. So there is very small region where LED emits light. So first of all, LED needs DC. And second, you can vary the voltage in very, very small area, about 2 to 3 volts, in order to change the brightness. If you give it a little more, what will it do? It will blow up. So as you can see, we can't dim LED with what we have coming out of our dimmers. So how do they dim? There are a couple of techniques. The first one is called PWM, which is pulse width modulation. LEDs react to power really, really quickly. You give them power, they turn on. You take it away, they turn off. There is no glowing like an incandescent lamp. So PWM is a turning the power on and off very, very quickly. The ratio of time between on to off determines the brightness. So in this example, we have 25% brightness. So we turn it on for 25, shut it off for 75. So this pulsing happens at a very high frequency, about 40 kilohertz. So our vision can't process it. We only see the dimmed output. This is good. This is the best way of dimming LEDs. But sometimes cameras will pick up on this pulsing, and sometimes we'll see it on a camera feed. Another way of dimming LEDs is CCR, constant current reduction. The amount of light emitted from LED is proportional to the amount of current flowing through it. So if we reduce the current, we reduce the brightness. It's also called analog dimming. If you can imagine it kind of like a valve. If you want more brightness, you crank it up. If you want it less, you kind of turn it down. This is good for cameras, but sometimes with the less current flowing through LED, you might get a different color of the light. So what is the difference between LED lamp and LED fixture? Anybody knows? So LED lamp, go ahead. Yeah, LED lamp would have an integral driver, and fixture would have general external driver. So this is what the LED lamp would look like inside. It would have the LED chip that is driven by the LED driver, some sort of heat sink to dissipate the extra heat, and a reflector to give you the right optics. So what actually does the dimming is the driver. Driver is sort of like ballast to a fluorescent fixture. It converts the incoming AC voltage into what LED needs, usually PWM or CCR, or sometimes both of them. Now drivers can be constant current or constant voltage. The manufacturer of the lamp usually puts it all together, so we don't need to worry about it. Now, one type of fixture can have many driver options, and the same driver can be used in a lot of different fixtures. So this is where the fun begins. I'm sure you guys have seen these fixture cut sheets. So if we look at this particular one, you got a few options here. Here are driver options to choose from. So we have standard 0 to 10 dimming with no mention of manufacturer part number. We have high lume ecosystem drivers with no part number. We have off-ramp dimming with no part number, and a DMAX dimmer, again with no manufacturer part number. Now if we click one of this, DM1 for example, we still can get 5 different drivers because we have different lumen outputs. So each of them will require a different driver. So we never know what driver is used in which fixture, because we have to have the driver in order to determine the compatibility with our dimming systems. Now it's a different story when it comes to LED lamps and transformers. I'm sure you've seen the MR16 lamps. So everybody are trying to replace MR16 halogen lamps with LEDs because they're so much better, they much less energy draw. But the problem here is the transformer that was in there before was designed for resistive load. It was not designed for LEDs. And LED does not create enough load in order to meet the load requirement for those transformers. So sometimes we have a really bad dimming performance because of that. And a lot of people don't realize that there is a transformer in between dimmer and a lamp, because sometimes transformers are just impossible to find in some of the retrofit sites. So yes, exact combination of a dimmer, lamp, and transformer all matter. Now let's see at look at some traditional incandescent dimming. I don't know if any of you guys have been earlier at the power class with Tom Steer. He covered a few of things about this, but if I repeat it, it just will get stuck in your head better. So, so this is how the phase cut dimmers work. So we have our sine wave, and then we introduce the dimmer to it. So what the dimmer does, it holds the electricity down for a portion of the wave. So less energy gets transferred to your circuit. So the longer it holds the electricity down, the less energy your circuit gets. So we have the forward phase and reverse phase. This example is the forward phase. So we wait part way through the wave and we turn our power on and do it every half cycle. So in this case, it's 25% light output, 50%, and that one is 75%. And my laser does not really work. So the forward phase dimmers usually use SCRs or triac, and they need a minimum load in order to fire. So forward phase dimmer would be this. This is D20 dimmer. It has a SCR in it. Chokes here are used for noise reduction, because as you can see right now in this example, if I wait partway through the wave and then I turn the power on, what does our filament do when it sees nothing, 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 and suddenly there is a lot of power and it starts to buzz, it starts to heat up. So it's, yes, 120 times per second you hear that. So chokes help with that. They reduce the amount of noise going to them. So the next is the reverse phase control. This one was designed for reducing the noise, because now we wait first. Oops, oh gosh. So instead of turning the power on every half cycle, we turn in the power off. So now our filament gets this nice increase, and then power just shuts off. So instead of going from cold to this buzz, it goes slowly and then it shuts off. So it's much less noisy. Reverse phase dimmers are usually transistor based. And transistor is very sensitive to current spikes and voltage spikes and temperature spikes. So there's a lot of electronics inside of the ELV dimmer to protect from all that. So if you can look at this one, this is ELV 10 dimmer. So there's much more stuff going on here. They're also more expensive to manufacture. They are designed for more capacitive loads like LEDs and electronic ballasts. Now look at this picture. So if you look at this area underneath the curve, that is the power going to our lamp. It's called RMS voltage. And we all know that voltage moves around during the day. Demand on the system is usually higher in the evening hours. Everybody comes home, turns on washers, dryers. Sometimes you sit at the dining room table and somebody turns on the elevator in the hallway and your lights do this. So we don't like that. So if we set our lights at 50%, we want it to stay at 50% regardless of what's going on with voltage. So our dimmers have this option called voltage regulation. What that does is when the voltage changes, for example in here it drops, our dimmer turns on a little earlier, and it still ensures that the same RMS power going to your circuit. So your lights always stay the same percentage, the same brightness. It is a great thing for incandescent lamps. Not so good for LEDs. In LEDs, this is how the LED drivers work. They're looking for this time on the wave to determine their dimming level. So for them, it looks like the level is constantly changing. They can't decide if they need to be at 50 or at 45, or at 50 or at 45. That's why we see the hovering. We're going to show you the example of it.
Go ahead and turn that on and I'll turn. Oops, room lights off. Not that button. You have this really fancy lighting system in here. There we go.
I don't know if it's not that easy to see because the lamp is kind of small, but you can see it.
Yeah, and this sort of thing, you're more likely to notice it out of your peripheral vision a little bit. So if you're not looking directly at the light, but down here somewhere, you'll notice it kind of moving around a little bit. And if the whole room worth of lights is doing that, it'll drive you nuts. And that is a frequent complaint. All right.
The other thing is LEDs, incandescents have very high thermal inertia because you have this filament that heats up and it masks any changes in applied voltage. Well, LEDs don't have very high thermal inertia. That's why we see any slight change. We get a lot of questions about sine wave dimming. People ask why LEDs don't work with sine wave dimming. I'm sure you can see why right now. Because LED drivers are looking for the specific time on a curve to determine the dimming level. And with sine wave, what we are doing, we're just changing the amplitude of the voltage to change the brightness. So there is no certain time on the wave. That's why they don't work. Now let's talk about inrush. Who knows what inrush is? A couple of people, good. So we all know that incandescents have pretty high inrush. This is why when we turn on the power initially, the filament heats up and it creates brief current spike. Well, the same is true for LEDs, but the reason there is capacitors. The moment you turn on the power, they start to charge, and that creates even higher current spike. The other good thing with LEDs, and good I mean like this, a lot of them have something called repetitive peak current. So it's basically mini inrush every half cycle. So every 120 times per second you get a mini inrush. The reason here is switch in power supply. So they turn on every half cycle and then get this little inrush. So they're usually 5 to 10 times higher than the drawn RMS voltage. So this is what usually kills dimmers early. Oh.
Okay.
Sorry. So it might be an easy question. So when you get 600 watt dimmer, for example, and you want to put 12 watt LEDs and you're figuring out how many you can put on a circuit, you might think that you might be able to put 50 of them because 12 by 50 is 600. Well, if it has an inrush like this, or if it has repetitive peak currents, the dimmer might think that it has a 100 watt load. And even if you put 6 of them on the dimmer, you already overload it. Another common issue with LEDs is capacitive effects. So if you look at these graphs, these show voltage and currents of the incandescent lamp. This purple line here is the Scr Turn-On Signal. Who knows what Scr stands for?
Yeah.
Good.
There we go.
Awesome. So Scr is kind of like a switch. It can be turned on at any point during a half cycle, but it can only turn off when both voltage and current are at 0. So with incandescent lamps, both voltage and current are in sync and the same shape. So they cross the line at the same time, the Scr turns off. Everything's great. Now with LEDs, because they're capacitive, our current leads voltage. So if you can see here, our current, this thing is just dying. So current, the blue one, crosses the zero line way before the voltage does. So when the voltage rises from zero, the current is still present. So it thinks that there is load. So SCR never loses its holding current. So that's when you see the flashes to full, or sometimes your load will get stuck at full because of that reason. We're going to show you a good example. First, I'm going to say that some of our product, or most of our product actually, has an option to change this window. So in this case, it's 500 microseconds. But if we change it to 1,000, a little bit wider, then both our voltage and current will be at zero at the same time. So we will fix that problem, and I'll show you how to do it. All right.
You can go ahead and turn it on.
There you go. This is a good example of flash into full. This is SCR misfiring. And now we're going to change blinking time. And now it fixed it. So if you run into a situation like that, that you think that your problem is misfiring of SCR, and it only happens on D20 modules, it doesn't happen on these, then the solution might be changing the SCR blinking time. And phone support can walk you through how to do it. The only thing is it's rack-wide setting. So if you change it, it changes for the entire rack, not just per dimmer. So it might affect other presets. So it might be like the last option that you might have to do. I had a question about Christmas light once, and they had a LED string of Christmas lights, and one of them burned down or something. So they replaced, and they never dimmed, and then replaced it with incandescent, and they start dimming. So they didn't know why. This is a typical example of ghost load. You add resistive load to the circuit, and it will start dimming because it will shift your current closer to the voltage. And yet another problem. So we get questions about the minimum load for LEDs on a particular dimmer. Well, there isn't really a hard number, because for LEDs, both the amount of wattage and the curve will matter. In this example, this is not a real example, it's just a drawn graph. You can see that the first example, it shows what the dimmer is supposed to be doing. The second one shows that the dimmer turns off early because there is not enough load in that part of the cycle. And another one is it turns on late for the same reason. And the last one, called the voltage distortions. These are actually real graphs, they're not drawings. The first example is 6 par 38 lamps. And that one actually didn't have any performance issues. But if you added more to a circuit, it would have. The reason for the voltage distortion is a choke. If you have D20 modules, you remember these chokes. So these chokes will interfere with electronic drivers and LEDs, and it will create those voltage distortions. The second example there in the middle is Chicago Field Museum, and it had 120 lamps on a single circuit. And that one had, its performance was okay, but the lamps were dying. So that's why we got involved and figured out. The third example is high lume, Lutron high lume drivers, and it was about 35 of them. So the dimming wasn't good, but we figured out the way to do it, to find a way to do it. So the reason we're showing you all these examples is so you know what we do and why we do it. It's very hard to predict how certain LED will behave on a dimmer, but if we take these measurements, we have a pretty good idea. Because we'll take some samples, we take some measurements, and we know you can put that many lamps on a certain dimmer. Because if you put more, you'll have inrush issues, or you'll have this voltage distortions or things like that. So we'll recommend how many we can put on a single dimmer. So what we have learned so far is what is LED, how it's supposed to dim, the best way to dim LED is actually not line voltage, it's to provide some sort of separate control signal. And Mark will tell you all about it.
Yeah. So, like we were saying, line voltage dimming is tricky, and there's really no product in that category that can perform as well as an incandescent lamp. The physics of it are just too hard, no matter how much, no matter how much money you spend on it within reasonable terms, you can't duplicate the way that an incandescent lamp behaves with an LED just by sending varying line voltage to it. So the ideal way of working around that is to give it constant power, or switched power, and have a separate control signal. And there's a bunch of different ways that, that we do that, or that LED manufacturers do that. The first one we'll talk about is 3-wire dimming. This is kind of a weird in-between one. So you have a switched hot and a dimmed hot coming out of in our products we would use a D20F dimmer module. So you get both the switched and the dimmed hot coming off the same circuit breaker. And so that uses power for, to power the electronics, and then it also uses voltage as a control signal separately. This is not real common. It's mostly Lutron that does this, and it's kind of a carryover from their fluorescent products as well. But these perform pretty well. They're not, they don't dim down all the way to 0, but they're better, they're more stable and more consistent and nicer fades than most line voltage dimming products. So that's certainly a good option. DMX, this is a theater crowd, so I would assume you've all at least heard of it and have some basic understanding of it. So I won't go into too much detail there. The main thing is it's a digital communication signal. You can have 32 devices. The type of wire that you use matters. Don't use microphone cable for your DMX fixtures. And you get individual control of the fixtures. And DMX fixtures can perform excellently. We'll plug our products, of course. They're perfect. You can do, good theatrical quality dimming, which is what we like to, or how we like to describe it. There are also really terrible DMX products. So just because it's DMX doesn't mean it'll work well. You know that in the theater market. That's true for architectural lighting as well. There are good manufacturers and there are not so good ones. But the nice thing there is that it's a well-established standard, and if the fixture manufacturer does their job and follows the standard, it will definitely be compatible with our controls, and everything will be happy. A related standard is RDM, which allows for bidirectional communication to the fixtures. So you can use the same wiring infrastructure and make configuration changes to the fixtures. You can address them and change their modes sometimes and see some status information. This is really common for architectural fixtures because a lot of times you don't have a user interface. There's no address wheels or LCD to set its address or mode, so you have to do it through RDM. The key thing here is that wiring, using the right wire, using good wiring practices, and terminating properly are very important for RDM to work properly. And paying attention to the number of devices on a run is important. We're used to with DMX, you can add an optosplitter whenever you want to have more stuff. That gives you another 32 devices. To a certain extent, you can do that with RDM, but once you get beyond that, you start to run into timing issues because the RDM messages happen in between the DMX level information. So there are very narrow windows between when the controller tries to talk to the fixture and when all of the fixtures have to respond. So our recommendation is to stick with 32 devices per output from a gateway or a console or whatever the control device is in the system. DALI is another digital communication protocol. It's not real common in the US at this point, although we are seeing it on some larger architectural jobs, commercial buildings. There's an airport that we did recently that the whole building was basically DALI control. It's interesting. It's you can there's some good things and some bad things about it. You can do 64 devices on a loop. Each loop has a separate DALI power supply. It's not in the fixture. It's not in the controller. It's usually a standalone box. The wiring is not picky. You can use pretty much whatever you want for it. You don't have to worry about polarity. You can topology free, meaning you can star off or daisy chain and do whatever you need to get the wire where it goes. Control wire class 1 or class 2. What that means is class 2 wiring has to be kept separate from line voltage wiring, which means more work when you install it. Whereas class 1 wiring can be combined with power circuits, related power circuits. So your power to the fixture and your control to the fixture can go through the same conduit. It's a little easier to install and cheaper sometimes. There are two approaches to dolly. Broadcast dolly means that everything on that loop, on that wiring run, all 64 devices, get controlled together. So you send one signal out and all of them dim up and down together. This is what we do in our panel products. So DRD, like that, and Echo relay panels, those are all broadcast dolly. You can also do individual control with, when the controller can handle it. So you can individually address each of the 64 fixtures on your loop and control them separately. We do that with our new response DMX to dolly converter, and we also do that within the Mosaic product family. The main thing that it has working against it is it's very slow in terms of sending messages from the controller to the fixtures. So in a performance setting, it might not be a good choice because you could end up with, in this room we have 3-4 different fixture types. They may all fade at slightly different times and rates when you tell them all to go to 0 if you're using dolly. Where, in a house of a theater, that would kind of look terrible. It's, different standards. So it's great for buildings where you're doing, energy management stuff. It could work well in a lobby setting, but it may not be the best choice for performance lighting. This is kind of what it looks like. You would have a D20 or an R20 module in the rack to provide control over power to the driver. There's a dolly option card in the bottom of the rack that provides a control signal, and then the separate dolly power supply that gets connected somewhere in that loop. Usually that would be provided with the fixture package or by the electrical contractor who's installing it. So pretty straightforward to do. Another approach to separating power and control signals is 0 to 10 volts or 4-wire dimming. This is another thing that is kind of a carryover from fluorescence that was pretty common for architectural fixtures. Because it's analog, there aren't really any hard limits to the number of devices that you can put on a single circuit. It'll depend on the specific drivers that are being used. And of course, the information you need to know to figure that out is usually not in the data sheets for those products. When we test things, we'll take measurements so we can get an idea of what the limits are on our products. But that one's really hard to find out without actually doing the testing and measuring it yourself. The wiring's not real picky, topology free, polarity matters. It is a DC signal, so you need to know which one's plus and which one's minus. As with dolly, it can be class 1 or class 2, as long as you're following all the rules for code requirements, using the right products to do that. You can run the control and power together. And this only ever works in a broadcast fashion like dolly, where everything on the loop is controlled together. Another thing that's kind of unique to 0 to 10 volt, kind of because it was a carryover from fluorescence, is a lot of the products don't go all the way to 0 with just a control signal. So if the product has a 5% or 10% minimum level, they'll go from there to full, but to get them to turn off, you have to cut power to it. So it's important that you can't just have a standalone 0 to 10 volt control, you also need power control as well. And there are two different ways of doing 0 to 10 volt, just to make it more interesting and confusing. Either way, it looks like this. We have a D20 or an R20 in the rack to do switched power. There's a 0 to 10 volt option card instead of a dolly card, and there's no external power supply. It's just the typically purple and gray wires going to the LED driver. So the first approach, or the first standard for 0 to 10 volt, is current sync, and we describe it from the perspective of the controller. So in this arrangement, the controller can actually be very simple. It could basically just be a resistor or potentiometer, because the driver is outputting a voltage and the controller provides a certain amount of resistance. The driver just measures what that resistance is. And this is most common for architectural fixtures because that's how fluorescence worked. So most 0 to 10 volt products for architectural commercial lighting use this, except for the ones that don't. Not in the theatrical sense, no. Because like so theatrical resistance dimmers, you were controlling the line voltage. Yeah, this is still, you have constant line voltage and then a separate low voltage control. But the control doesn't have to have any electronics in it, and that's why it was popular originally. Of course, ours are all electronic, so you can control them via DMX and whatnot. The nice thing about this is there's a quick and easy test that you can do. One, to identify that it's current sync, and the other to kind of tell if things are sort of working. And that's that if you take away the controller, you give the driver power, but leave the 0 to 10 volt wires open, it should go to full. And then if you short them together, it should go to its minimum level, 5%, 10%, or 0 if it does that. So you can see a little bit, that tells you to a certain extent whether things kind of work and whether they should be compatible with our products. So here too are panel products like DRD, Echo Relay Panel, and our older Unison products are all current sync control. The other approach is voltage source. In this case, this is what you might sort of, if you're old enough, have passing familiarity with as the theatrical style of 0 to 10 volt, where the controller is actually outputting a voltage and the driver is just looking for that voltage on the input. So 0 volts means off or minimum level, 10 volts means full. In this case, if you disconnect the controller, the driver should be at its minimum level. You can't test it just by shorting the wires together, but you can use a 9-volt battery to get it somewhere close to full, just as a quick test. Polarity matters. I'll say that again. If you swap an entire circuit's worth of polarity, you can get something really interesting, which is basically that it dims backwards. So as I move the fader down, the light goes up. As I move the fader up, and I can't do this looking at it, the light goes down. So that's an indication that, in this case, you only have one fixture on the circuit, but if you had multiple, then probably the whole circuit is backwards. If you mix up just a couple of fixtures on the circuit, that may be stuck at full, it may end up being stuck at its minimum level, or it may do something like this, or it may freak out a little bit. So something to, just some troubleshooting tip there. Another thing we've run into is that some drivers have a poorly designed power supply inside of them that will leak AC voltage on the control wires. That can potentially damage the controller on our end of the system. If it's bad enough, it may also interfere with dimming performance. So you may see that as flicker or shimmer because of that changing AC voltage on the control wires. And sometimes when you're running the wires as class 1, all in the same conduit, the electrician might forget which black wire is for the hot and which black wire is for your 0 to 10 volt common or whatever. So that's just something to watch out for. Again, you can very much blow stuff up if you make that mistake. But basically, just because it's low voltage, don't treat it as it's safe, because it may not be. There may actually be line voltages present on those wires. So ETC offers compatibility testing to help you figure all of this stuff out. It's a free service. You send us this stuff. We test it across all our products, and we generate a nice report to show you how it did and what the best settings are to use with it. We try to get results within 2 weeks of when we receive it. Sometimes that depends on how busy we are. If all of you send a bunch of stuff all at once, it may take a little longer. We do put everything, all of the results for everything we test go on our website that you can all look at. So you can use that as a resource to see if we've already tested something. And see how well it did, and also to see the results of your test if you do send something in to us. That link will take you to a page that has a form with information on what to send to us, what information to include with it, and all the details of our testing process. The online list, results that go onto it expire after a year because we assume by that time the product has changed and the test is no longer valid. If you buy something today that we tested a year ago, it's very likely, even if it's the same part number, model number, manufacturer claims it's the same, it's very likely the electronics inside have changed, and it'll be different. It might be better, it might be worse, but it's probably going to be different somehow. So that's something to watch out for sure. Why not test it yourself? You are clever people, you have dimmers, you have lamps, you know how to connect them together. A big thing is that the test isn't valid if there's a mix of incandescent and LED on the circuit. And that's from an electrical standpoint. As we were looking at all of the stuff that Natalia talked about, most of those problems get worse as you add more LEDs onto the circuit. So if you take all of the incandescents out and put one LED in, it may work, but then when you add 10 more, it may not. Or even worse, if you leave all of the incandescents in and put one LED in, the electrical characteristics of that circuit are not the same as if it were all LEDs, so it may behave better. It's also not valid because of how your eyes work. So we looked before at this shimmering light, and when that light is by itself, you can see it twitching a little bit. But if you have a mix of incandescent lamps that are stable and that LED that's shimmering a little bit, you can't perceive that as much. Your ability to perceive flicker depends on how much flicker is happening relative to the total amount of light in your vision. So if it's not a completely dark room with that LED as the only light source, it's not going to look the same as it will once you replace all of your LEDs. And I didn't change anything. The LED is still at the same level. You just can't see it as easily once the incandescents are kind of drowning it out. And it's the same thing with noise. If there's a soft noise going on in the room and somebody starts playing a trumpet, you may not hear that whisper anymore. Just a visual test doesn't tell you about all of the electrical problems that Natalia told you all about that are going on under the scene. So it may seem to work, it may initially work, but there may be failures down the road because of that voltage distortion issue. That was the complaint, is that individual lamps were burning out because they were getting those really huge spikes of voltage that they just weren't designed to handle. The other big advantage that we have is all of our products in one room. So we can swap dimmer modules and see if it behaves better. We can take our CEM Classic and put a CEM 3 in instead and see if that makes a difference. With some products, the CEM 3 obviously newer, fancier, better, has lots of new features that can help compensate for some of the behaviors that LEDs do. But that won't necessarily fix it. So we don't want you to spend money on an upgrade if the LEDs that you bought still aren't going to work after you spend all that money. We want to get your money, but we want you to be happy as a result of getting that of us getting that money. So this is the compatibility database. It's broken up into categories: manufacturer, model number, voltage, and whatnot. So you can sort, if you're looking to check on a particular lamp, you can sort by manufacturer and part number. If you want to replace all of your PAR 38 lamps, then you might want to filter by lamp type. The wattage that's listed there is the nominal power draw of the LED, so how much power it actually uses, not the incandescent equivalent that some manufacturers like to put on it. So that's the actual power draw. And then the different kind of dimming, if it's 0 to 10 volt, line voltage, or DMX or whatever. So you can choose those categories and then hit the search button and you'll get a list. If you're really picky, you might only have one result in your list. What we get for testing is kind of just a random sampling. So we may not have something that fits your needs exactly. It's it's kind of a toss-up. There are just so many LED products, we couldn't really go out and test all of them. So this tells you when we tested it, who the manufacturer is, part number, what kind of lamp. And then on the right, there's the click for results, which gets you a really brief sort of summary view that shows two main things. The fade performance is all blank because we don't have that part of the test established yet. I'll talk more about that in a little bit. But the minimum stable level is how, from full down to what level can it dim, and when it's sitting at a level, not flicker or shimmer or do anything undesirable. This particular example is kind of mediocre, 50%, 30%. And then there's a blank for the legacy D20 because it probably didn't work at all. I think that one was an SCR zero crossing issue, so it just gets stuck at full as soon as you try to dim it up. So you can go through this to kind of as a filter to get rid of the really bad ones, and then hit the report button to get more in-depth information on how it performed. So the report will start out by having a nice picture of the lamp and some details about what it is. Well, there's two things to note. We put the nominal power, which is what it says on the box, and we put the measured power, which is what we found that it actually did. Often they're pretty close, but some are surprisingly different. We don't really investigate that further. We just put what we measure, and if you want to bring that up with the manufacturer of the lamp, go for it. The other really important number here is the quantity that we tested. For anything line voltage, we like to see a decent number of them. We request 4 to 6 at least, so that we can do different combinations. You do 1 lamp, 2 lamps, and see how it changes so we can anticipate some of those additive problems. So in this case, there were 10 of them. That's good. We can make some pretty accurate guesses from that. If we only get 1 lamp, then it's not going to be as reliable of a report. We'll still put it out there because it's better than nothing, but there's no guarantee that you won't see it change a little bit when you add more lamps to the circuit. And then for each dimming type, dimmer module, and so in this case it's a sensor 3 ELV10. So the rack type and the dimmer module type. You'll get a little report card like this. So we'll list the minimum stable brightness. At this point, we're describing the fade performance as kind of just a subjective observation. The dimmer settings that we use that were the best performance that we found. There's a limit to how many you can put on the circuit, and then what the inrush characteristics were, and any other notes that we would include. And then there's a chart on the left, which has a lot of information going to it. So this is the static level performance. The dotted line shows the brightness at each control level from 1% to full in 1% increments. So when it's sitting at a level, that's how bright it's going to be. And then the solid black lines show how stable it is, or how likely you are to notice that it's flickering or shimmering or doing something undesirable. The scale here is at the bottom of the chart. You definitely will not notice it. At the top of the chart, you definitely will notice it. And way off of the top of the chart is strobing like a disco. So there are there are values that are much worse than are, it's just once you can definitely notice it, that's 100%. So it's a probability of how likely you are to notice something unappealing. And just to explain that a little bit more, this is an example of an incandescent lamp, 150 watt, par 38, like one of these. So you can see it has a nice, even square law curve. It's very stable in the sense that the solid black lines are at the bottom of the scale. And it's very consistent. I missed that on the previous slide. The distance, because LEDs don't always do the same thing all of the time, we run the test multiple times, and then we plot the highest and the lowest values. So if there's a wide gray area, like there was on this one, that means that it was different from one test to the next, which means it could actually be a little bit worse than this sometimes, or a little bit better than this sometimes. So it kind of tells you in that range you need to be a little nervous, even though the values are kind of low. So in this one, the lines are close together, there's not much gray, and they're low values, so it's stable and it's consistent. So that's a good lamp. This is an LED. One of many ways it can look interesting. So the curve has some irregularities into it. There's a little knee at the bottom around 5%, and then it reaches full brightness at about 87% control, and then it actually goes down a little bit. You don't really notice that. That looks like it's still at full, but the main thing is that as you're moving your fader up, it gets to full before you're done moving. So that's a little bit weird. You can also see the wider gray area means that it was inconsistent from one test to the next, and higher values mean it had a more noticeable shimmer or flicker. We don't really try to describe what it's doing. It's just doing something you don't want. That's the main takeaway from that. This has a very similar curve, but it's more stable. And once you get above 20 to 25% brightness, then the value of the flicker is low enough that it's probably not going to be noticeable, and it's more consistent. You have almost a solid line there, so it's more predictable. So, maybe not something you want as your house lights in a theater, but it would work great in your lobby where you just want to dim them sometimes, and that would be fine. This one has a really weird curve. So there's this really steep part in the middle where a small change in control level makes a big change in brightness. And that can make it very hard to set it at a specific level. And then you've got that part near the top where it changes very quickly. So this one is definitely not one that you would use, well, for a lot of applications. For anything where you'd be changing the level. If you can set it and leave it there and get it exactly where you want and not mess with it, it might be okay. And it's got some flicker in the lower end of the dimming range as well. So all of these tests are, the criteria of is it noticeable or not has some pretty complex math behind it, and it's based on some research from the Lighting Research Center, as well as stuff that we've adapted to more specifically fit the kind of testing that we do for dimming LED products. I'm not going to go into how we calculate that. That could be a very long class on its own. But if you are interested, feel free to contact me, and I can get you some more information on that. It's interesting if you're into that sort of thing. Another important thing is that this is measuring directly human perceptible flicker. So something where when you're looking at it, you can see it doing something undesirable. It doesn't address camera flicker, and it doesn't address stroboscopic effects or the things that can cause headaches or other irritation. That's outside the scope of this test anyway. So part of the reason this is really complicated is that the light coming out of the LED is complicated. As with incandescence, there's always going to be, or often going to be, some ripple at 120 hertz, so twice the 60 hertz line frequency that normal power is at. But that's not something you can see directly as long as it's a small enough amount of ripple. So like the first two examples, assuming that's all they're doing, those wouldn't necessarily be a problem visually. You wouldn't notice that. The third picture there shows the light turning almost all of the way off at 120 hertz and then turning back on. You still can't see that directly. So that's actually this lamp right here. And when you're looking at it, it seems like it's on and stable. But in terms of stroboscopic effects, if you're moving or if the lamp is moving, you see kind of the, it looks like stop motion. So if the lamp is moving or if you're moving in front of it quickly, you see kind of that still motion. This can also be really irritating to people. So like as you're moving through the space and this is happening, it can kind of mess with your perceptions a little bit. It can give people headaches and just be generally undesirable. But again, that's not what we're measuring with these tests. What we're looking for kind of looks like this. So you see that 120 hertz ripple, but it's also bouncing around a little bit here and there. And that's what we're trying to separate out from the normal ripple in the light output.
Are those some harmonics? Is that a harmonic of 60 hertz?
It's not. Well, to a certain extent, it's related. As you know, when we were talking about earlier about voltage regulation, even when we turn that off, there's a little bit of variation from one cycle to the next of when the dimmer turns on. So if the LED is trying to react to that small change very, very quickly, then the light output will change. It's a little bit random, though. It's not actually in sync with the line voltage. But you can see that because it's happening at a low enough frequency that it's in your visual range.
Is this relative to LED tape very much as well? I mean, this is all. So the testing that you've done is it. Would that apply to LED tape as well, or is that
Sure. Yeah.
a different thing?
It is, and we have an example of that here. It actually, so this is a tape product going to a Lutron driver that actually works really well. But a lot of times when you're using this kind of product, you're using it with a magnetic transformer, a very simple power supply. And those are the ones that are more likely to have an output that looks like the chart on the right there, where it's actually going from on to almost all the way off. And then you're more likely to see that stroboscopic effect.
And that would be true across multicolor LEDs?
Well, those would be a little bit different because they're usually DMX controlled. So then it depends on how well the driver is designed as to how well it's going to work.
There's a lot of this.
Oh, sorry.
There's a lot of this. I kind of assume these are also commercial white LEDs, but if you
Yeah.
take that into the different color LED realms, is that?
It certainly can be an issue as well. Most of what we test really is the line voltage dimmable white LEDs. When you're talking about color products, it's going to have usually DMX control. So from our standpoint, there shouldn't be any compatibility issues. It's just a product performance issue. So you can take that and test it on your console, and it'll do exactly the same thing, hopefully, whether it's one fixture or 30 fixtures. You know, as long as they're following the standard, it'll be consistent. So we will test that if you want us to, but we get a lot less of that because in theory, there should be less problems or fewer problems. Yep.
Are other manufacturers
This kind of testing? So yeah, sort of. That quote, what's that? For the consumer? Yeah, well, right. So if you go to Lutron's website, and they make dimming products as well as LED drivers, they do have a list of lamps, and a lot of what they put on there is actually like wall box dimmers, the more consumer level products. So they do have a list of lamps that they test with their dimmers. They don't have the same level of pickiness that we do. So they will say dimmable, and that might mean that it changes levels, but it may look terrible while it's doing it, and it may not dim as much as you want. It's very vague. This is kind of something that is new and that we're developing in the sense of having this metric. And to give a little bit of backstory, up until about a year ago, most of our testing of compatibility, aside from the electrical measurements of what's going on the power lines, was somebody sitting in a dark room and staring at the lamp and saying, I think it's flickering now, and if I move it up a little bit, it's not. So this concept of having a test fixture that measures the light coming out of it and does some fancy math and comes up with a value of perception that is consistent and not just dependent on how tired the person sitting in the dark room is. This is kind of new, and it's something that we're doing certainly to a greater extent, I think better, as a personal opinion, than any other manufacturer of dimming products and whatnot. So yeah, it is a little bit special and new. Ideally, this would become an industry standard, but that'll probably take a while. We're definitely not there yet. But anyway, getting back to, so the brightness measurements is another point of potential confusion because the way a light meter works is not the way that your eye works. All of the reports as well as the LED fixture specifications are given in terms of how a light meter works. So if it says it's a 10% minimum level, that's measured. That won't match your expectations. So if we've got these two incandescent lamps, right now they're at full brightness. Right now, this is at 10% of full brightness as measured by a light meter. This is what your eye perceives as 10% brightness. And then this is 5%. And this is, if I can hit the button, that one is 1%. So if you see a driver that says it has a 1% minimum level, this is what it means. And going from that to off may still be a big step. So it's important to know how the specs are called out and how your eye actually works. And note, this is actually not 1% on the fader. I think it's actually about 7%. You know, with the incandescent lamp, you can dim down like way below 1% perception level, which is necessary to get a nice, clean, gradual, theatrical fade up from 0 or down from full without being a little bit jarring. Fade performance, working on it. And actually very close. This is something that I've been spending a lot of time on over the last several months or years. It's going to be a very similar metric to the static level stuff of, is there something noticeable that you don't want to have happen? Is there a step in the fade? Is there a big jump when it turns on? And it's going to be a similar scale of, you won't notice it to, you definitely will notice it to, it just snapped from 0 to full in 0 seconds. So this is kind of a sneak preview of that. This is what an HPL 575 with default settings and a D20 looks like for a 5-second fade. The blue line is the brightness over time, and the red line that you almost can't see at the bottom is that perception value of how likely you are to notice it doing something not smooth. This is our gold standard of what we expect for good quality dimming. This is one particular LED. This one is a really interesting example because it's actually smooth in the sense that you don't see little steps as it's fading, but it's got a really weird curve. So there's a big bump as it first turns on, and then there are these spots where it kind of speeds up and slows down as it's fading. And this one I actually have here to show you. It is this lamp here, so we're going to do a 5-second fade, and it bumps on, and then kind of, as it's going up, it has those spots where it looks like it pauses a little bit, and then as it fades back down, it does the same sort of thing. So in some ways, it's a really good lamp because of how smoothly it fades from one level to another, but it's still not something you would want probably for your house lights. I'm just going to leave the lights for a moment. This is a different LED, and it shows, I don't have this one as an example, but it shows a difference between a setting that we have called smoothing mode and not having that on. So this is a setting in DRD and Sensor 3. It's also always on. You can't turn it off in the dimmer that goes in our Echo relay panels. So the first one shows without smoothing mode. There's a big bump as it turns on. That's pretty common for anything line voltage. And then there's some steppiness as it's fading up. So you see that perception value, and it gradually goes down because those steps are less noticeable as the lamp gets brighter. And then on the right, the bump as it turns on is a little bit less significant, and then the fade up is is smooth. Now this one does have a weird spot in the curve, around 80% or whatever that is. The interesting thing about that, you notice there's no red bump there to show that something bad happened. And the reason for that is your eye doesn't really see it that way. When it hits that point, you think it's already gotten to full, and you don't notice the rest of the fade after that. So it looks like it's just completing the fade early. This one is another interesting example. It's our source forward with line voltage dimming. So the chart on the left is what happens when it fades up from being completely off, no power on the circuit. As with any other line voltage dimming product, it has electronics inside of it that need power before it can start doing something. So when it gets enough power to actually function, then it catches up with the fade very quickly and then does relatively nicely from there. The chart on the right is what happens if you go to a preheat level rather than completely off. So the fixture at that point is not outputting any useful amount of light. If you're looking directly in the lens, you can kind of see a glow. But when you fade up from there, it doesn't have that snap at the beginning. So this is what happens when you go from off with a 5-second fade. And then if we do a fade down to the preheat level, like an incandescent, it kind of emulates that fade, that last little bit of fade to 0. But at this point, you can't see any useful amount of light coming out of it. But when you do a fade up from 0, it's a lot more gradual. And this is kind of something that's unique to our product. Not many other manufacturers do this. And some of that is because most of the line voltage products are not targeted towards theater, where the user would be clever enough to do something, to program something like this.
Pardon me, what is that preheat level? Is it like 03 or is it?
It depends a little bit. So it's going to vary somewhat depending on things like how many fixtures you have on the circuit and how long the wire is, how much voltage drop there is from the dimmer to the load. So it is something you have to experiment with a little bit to figure it out. But once you figure it out, then you can always go to that level and it'll be consistent.
Because that's a pretty big fact right there. The fact that you can preheat it and have it fade smoothly from 0.
Yep.
Just that fact alone would mean that you make the choice to go with line voltage source voltage instead of.
It makes it a lot more palatable or tolerable than it would otherwise be. And it's something, it does take a little bit of extra work to program into your cues to make sure that when you want to do a nice fade next, that it goes to 1% or whatever it is, and whatnot. But once you do that, then the performance is much more similar to an incandescent.
Question about that.
Yeah.
It was just a set a curve on those fixtures, or would there be a problem with that when you set it 7 times?
Efficiency. So yeah, you could set within the dimmer rack to tell it to. So there is actually a setting called preheat in the dimmer rack where it always goes to that level, but doesn't turn all the way off. And you could do that, but it is drawing a little bit of power in that state, so you may not want to. That's where you may want to have it on the control side so that when you're using it in the middle of the show, you can go to that level. But at the end of the night, you can turn it completely off and not be wasting that little bit of power.
I think I recall it was a way to set for this console.
Yeah, exactly. Yeah, you can have it so that 0 on the console is 1% or 3%. In the back?
Correct me if I'm wrong, but if you're setting curves at the console level, that would apply if that channel set a null value, or would only apply if that channel set a 0 value?
That gets into console programming that I'm less familiar with.
You're right.
But Sasha knows more about that. Good. She's in phone support, so she knows how to answer those questions. But yeah, so I mean, basically, it's something that you do in programming. You can make it work when you want it to. You can make it go all the way off when you're not going to use it for a while. It's fancy and cool. And like I was saying, the majority of line voltage LED products are not targeted at us. We're more picky than their normal application. So they don't build in cool features like this, just something that would be a screw-in replacement lamp. So that's mostly us. Okay. LEDs are complicated. Main takeaways from this, you saw all of the electrical characteristics and problems that can happen, and all of the various other control issues that can come up. There's no guarantee at this point that something that says dimmable on it actually will dim the way that you want it to. All that really means is that somebody in marketing decided to write dimmable on the box. At some point in the future with the NEMA SSL7A standard, once that actually gets established and people start using it more, it'll help, but we're not there yet. Line voltage dimming is the hardest. there are no line voltage dimming products that can completely replace incandescents. Even ours, which is really cool and fancy and the best thing ever, buy our stuff. No, it still isn't perfect. You have to it can get pretty close if you use it just right, but it takes a little extra attention to make it work pretty well. So separating out power and control, still no guarantee. The product still has to be good, but your odds are much better of getting desirable results. We're here to help you. We want to help you, and we want to help you before you spend a lot of money, because you're usually happier that way if we know it's going to work before you spend a lot of money. So check the database, give us a call, send us an email if you're looking at doing upgrades or replacements. We can tell you if we've tested it already. We can give you good information on it. If not, we can get it tested and then come up with a plan for how to make it work, or whether you should look at a different product. Another one is what I was getting at with in the database. The results are only there for a year because things change very quickly. If you find something that works, you want to plan for it not being available in 6 months or a year, or the next time you order next week. So once you make the decision that this is the right product, you want to make sure to also order spares. LEDs last forever once you put them in theory. But in a lot of, and especially in the realm of screw-in replacement lamps and other products in that category, you can expect to see some failures in the first year. 6 months, 3 months, somewhere in that range. If they survive the first year or two, they'll probably last 10 years. But there will be some initial failures, and if it's a year later and you don't have spares, then you're going to put something in that doesn't match. It may not match visually, it may not have the same electrical characteristics, it may not be at the same level when you set the dimmer the same way. So you want to plan ahead and get more than what you need immediately. So that's our presentation. If anybody has any other questions, this would be a great time for it. You can ask all the questions you want.
I've never heard of your forward phase dimmer. What other purposes would that have? Other than just making it tungsten film and quieter?
Having the chokes in it, you mean?
Forward phase.
Oh, well, this was, so the D20, a reverse phase. Oh, okay. So this was originally designed for solving problems with low voltage incandescent loads, where you have an electronic transformer for like a 12-volt MR16 lamp or something in that category. Because a lot of times those electronic transformers had some of the same problems that LEDs do now. They were capacitive loads, so you could get that effect. And some of the other challenges that we have with LEDs first started with that. So that's why we already had this product. And then we've done some things from a hardware standpoint. And then we've done some things in the controller with software to make it work even better for LEDs.
So it's really for capacitive load as opposed to...
For LEDs and electronic, yeah.
We're using D10s right now.
Yeah.
Yeah, it's pretty good. I got two different style of lamp though, so I guess a little dicey.
Yeah, right.
I haven't bought any more spares yet.
Oops. Yeah, and actually, I guess that's something I should probably add somewhere in here. Yeah. Because of the way that LEDs can be different, you really want to try to avoid mixing different types on the same circuit.
We have some variation in
if you can,
put in.
Yeah.
Yeah, there were some that just popped on and 1% full. They're work lights right now.
Right.
we did have to call them in.
Yeah, exactly. Cool. Any other questions? All right. If not, don't forget your course evaluations. Also, this is one of the ETCP credit classes, so make sure you sign up for that over here somewhere. Hey, there we go. So if you're going...
Different one for every course.
Right. So if you're going for that credit, make sure to put your name down.
I don't care. Where do you want to do it?
So I just put it in.
Yep, and also at the top, I promise to mention it every time.
I'll just leave it off because it'll be here anyways.
You can hide it somewhere.
How much more is that?
No idea.
We don't know prices.
Yeah, we don't usually deal with pricing.
Doesn't look like it.